Welcome. This is Chuck Ridgway, Automation Technology Manager here at Horner. Thank you for joining us for another Tuesday live stream. And I'm pretty excited today because I've got a topic that I think a lot of you probably aren't all that familiar with, but you really should be. And today's topic is using J1939 protocol with the Horner OCS. So J1939 is a protocol that some of you may know is used on basically every automobile and piece of mobile equipment out there, but a lot of you probably don't know a lot else about it at all. And joining me today to introduce J1939 to you is Mr. Casey Gardner. How are we doing, Casey?
Hey, not too bad. How's it going, Jack?
It's doing great. Well, as I mentioned, of course, a lot of people know that J1939 is a protocol that's available on cars, it's available on all kinds of vehicles, but there's lots of other applications for it as well. I'm sure you're aware of a few.
Yeah, I mean, it's kind of like you said, it starts on just about anything with an engine kind of attached to it or using it in some way. So things like backup power generators would be something. Agriculture, you've got your tractors and harvesters and all sorts of agriculture equipment that would be part in there. You've got mining equipment. There's all sorts of different military applications for it. So I mean, it's just a wide spectrum of things that it applies to.
Absolutely. There's a couple more I can think of as well. Shipboard applications. You know, you've got diesel engines on tugboats and other similar devices. And also another good one, it's kind of related to agriculture. Let's say that you've got a remote location, you need to do some pumping, whether it's for irrigation or something else. You don't have, electricity handy to do the job. A diesel-powered pump is a way to solve that one for sure. So lots of applications. Okay, so today while I'm giving the material, Casey will be manning the chats as he always does. If you have any questions, don't hesitate to chat them in. Casey will either answer them during the presentation, or he may save them for later so we can discuss them when we bring Casey back in. So again, don't be shy. All right, let's go ahead and get started. Okay, using J1939 protocol with the Horner OCS All-in-one Controller. Let's take a look at our agenda. Of course, we're going to introduce what is J1939. We're going to talk about the messaging. Now, we're not going to go too deep in the weeds. What we want to do today is give you a really practical understanding of J1939 and the way you would typically use it as a control engineer. And so we will need to get into the messaging, but again, not too deeply. Of course, we'll also talk about Cscape configuration because like any other network, J1939 needs to be configured. Now, one thing that's a little different about J1939 is it packs a lot of data in relatively small packets. So after you receive it, in some cases, actually in most cases, there's quite a bit of massaging that you need to do to the data to unpack it, to scale it, to convert it to engineering units, those sorts of things. So we're going to go through all of that with you today. So that's what we're calling decoding J1939 data. And then as always, we're going to do our best to give you some really good demonstrations. We're going to pull some parameters off of J1939, stick them on the front of an OCS, go through the entire process just like you would in your application. Okay, so what is SAE J1939? Well, let's start with the SAE. SAE stands for Society of Automotive Engineers, which is an organization that has since changed its name to SAE International, but it's the organization, the trade organization, that put together the specification for this higher level protocol for communications and diagnostics among vehicle components. The spec was first released around 2000, but really for years and years before that, specifications were in development, because back in the mid-90s, it was pretty much dictated that any vehicle that's released from that point forward needed to support J1939. Now, like a lot of networks, including Horner's own C-SCAN network and CAN Open, a field bus network, J1939 uses CAN as its physical layer. So it takes advantages of all the capabilities of CAN for robustness, etc., using that as its physical layer. And because of that, because it uses CAN, I would say that J1939 is largely responsible for the hundreds of millions of CAN chips and devices that are sold annually worldwide. So this is not some obscure network that nobody uses. This is probably second only to Ethernet, one of the most common networks available in the world today. And as Casey and I mentioned in the opening, it literally has dozens and dozens of industries that utilize it, including, of course, automotive, which we've touched on extensively, but also agriculture, construction, fire and rescue, fire trucks. All fire trucks have J1939. Ships, again, shipboard applications, whether it's tugboats or cruise ships and everything in between. Power generation, pumping, military applications, all over the place. It's used in a lot of different places. So as a control engineer, as you branch out into other applications, you'll be surprised at the cases over the years where you'll run into J1939 as an option for extracting data from a piece of equipment without having to set up parallel instrumentation and parallel I/O. Okay, so now let's get into a little bit in terms of how J1939 works. And as I mentioned before, we're not going to get deep in the weeds on this today. We're going to give you some good practical information. So like a lot of communications networks, J1939 is also based on the 7-layer OSI model, and CAN takes care pretty much of the lower 2 layers. Okay, and then you'll see on the second column of that diagram there, you'll see listed some J1939 numbers. And what those are different specifications that define different elements of the model or different elements of the protocol. Okay, from the physical layer up through the network and transport layer, all the way up to the top to the application layer. And that's where we're going to focus today, is the application layer, because that's where the useful data can be found that as control engineers we can use to interface with our control equipment. Now, from a messaging standpoint, J1939 fully takes advantage of all the capabilities of CAN, and it's a true peer-to-peer protocol, and it's a true broadcast protocol. So with peer-to-peer type messaging, you can have one-to-one type communications among pretty much any nodes on the network. On a broadcast type scenario, it's a one-to-many. So one node can broadcast information to the network, and then any nodes that are interested in it, that data, or specific pieces of data, can choose to snoop on the network and accept that data in. Okay, so in that way, it works very similarly to CSCAN protocol, which we've talked about before. CSCAN being Horner's proprietary CAN-based protocol that's used for remote I/O as well as OCS to OCS communications. So just like CSCAN, J1939 takes advantage of broadcast capabilities and peer-to-peer type communications, which is very efficient. Now let's take a slightly deeper look, and let's take a look at a J1939 message, which is diagrammed out there on the right. So the first part of the message is a 29-bit identifier, and buried within that identifier there is 18 bits, a little over 2 bytes, of something called a PGN. It stands for parameter group number. Now the data attached to each PGN that makes up the other part of the message is 64 bits or 8 bytes of data that's called, or that contains, suspect parameter numbers, or SPNs. And SPNs are really the key data that's exchanged over the network. So that's really the data that we're after, is the SPN data. It's contained within the J1939 message, and it's contained in the data portion of the message after the PGN, which is made up from the 29-bit identifier. Okay, now in most applications, when you're using J1939 with the OCS, effectively what's involved is acquiring data from an engine or another component that supports J1939. Much of the data that we're looking to acquire is broadcast automatically by those other devices on the network. So the OCS literally can just snoop on the network and get the data it needs when it comes to receiving broadcast data from other nodes. Now the OCS has much more capabilities than that, even though receiving in broadcast information is by far the most common task. The OCS is also capable of requesting data to be broadcast from other nodes that's not automatically broadcast. The OCS is also capable of transmitting data itself. Okay? Today we're going to really focus on receiving and interpreting broadcast data, probably in a future live stream, we'll focus a little bit more on the other aspects of messaging on J1939. But today it's going to be all about receiving that broadcast data that other devices on the network are typically broadcasting on a regular basis. So the overall process when you're looking at applying the OCS with J1939, the first step is, if possible, acquire a copy of the PGN and the SPN list. Remember the parameter group number, and the SPN is those critical parameters that we're interested in. Get a copy of that list from the equipment manufacturer if possible. Now, if it's not possible, then get online and get a hold of kind of the standard PGN and SPN database that's available that has all the industry standard parameters, because a bulk of what you're looking for is probably just industry standard anyway. Now, once you've got that document, whether it's a spreadsheet or something else, find the specific parameters you're looking for. Again, they're going to be SPNs, and then find out which PGNs they're part of. Once you've identified the PGNs that you're going to need to take in, because it's got the data you're looking for, configure the OCS to receive those PGNs that have the data that you're interested in. At that point, once you're configured and running, you should have blocks of data coming in as PGNs. From that, you should be able to extract the SPN parameter data that you're interested in and then scale it as is appropriate to get the engineering units you're looking for, whether it's a temperature or pressure or something like that. So that's the basic process. Okay, now which Horner OCS controllers support J1939? Remember, OCS stands for Operator Control Station. OCS is the Horner's brand name for our all-in-one controllers. They combine the functionality of a PLC with an HMI, with networking capability and I/O capability, both built-in and remote. And J1939 is certainly one of the networking capabilities that's available with the OCS. Now, if you're looking at a single CAN model of OCS, something like maybe our XLE or XLT, or our XL4, EXL6, EXLW, the X5, RCCs, those are all controllers that support J1939. However, it's optional. So you need to order from the factory a part number extension that includes J1939 firmware loaded at the factory, or with newer firmware, you might be able to upgrade one of those products in the field and acquire a license for a one-time upgrade to J1939. So a product that's on this list that you see here that's got a single CAN port, it can only support J1939 and not other protocols simultaneously on CAN. So if you're getting J1939, you're not getting C-SCAN or any other CAN open or any other networks, okay? But you can place that order, get that single CAN port model. Now you'll notice it's not supported in the micro OCS series with the exception of the X5. So the X4, X2, X7, X10, those products do not support J1939 because it's one of those extra protocols that is not included with that entry-level product. Now for our dual CAN models, XL7, EXL10, XL Plus 15-inch, on CAN 2, the second CAN port, you can select J1939 during configuration. So those are included as standard. So there's no extra charge for J1939 support on the dual CAN models. Okay, next let's get into the configuration for J1939 in Cscape. Okay, and it's really very straightforward. We'll cover it here with a few slides and then we'll go online with Cscape and show you how it's done that way. Okay, so you start out in the Hardware Configuration tab and you go down under the available protocols for either CAN 1 if you've got a single CAN product, or CAN 2 if you have a dual CAN product. And on that list you should find J1939. Once you've selected J1939, press the config button next to that port. The next step is to assign a variable or a group of variables to actually act as the control and status for the J1939 network. And that typically, if you choose the most common option, is going to be a series of 10 consecutive variables, word type variables. All right, and we'll go into those details in a second. But before you assign the specific variable that you're going to use to control and monitor the network, the first step is really to select the default message database, which today there's really only one to select, and that is manual definition. In the future, we're going to be adding some additional databases as an option from that pull-down list. Today, the only one that really makes any sense for applications is the default message database, manual definition. And then the other thing you'll do would be to select the network baud rate. Now, the default for J1939 is typically 250K, although we do also support 500K because more and more devices are starting to use that baud rate. All right, once you've done that configuration of your default database and your baud rate, next is when you select your control structure variable. Now, if you're using standard register-based logic, what you're going to configure is the starting register of a series of registers that's going to be used for control and for status. If you're using variable-based logic, you're probably going to assign a word type variable that's dimensioned as an array as your approach. Now, you have two options here, regardless of whether you're talking about register-based logic or variable-based logic. If you're just interested in standard PGN mode, which is the capacity of 15 transmit PGNs and 15 receive PGNs, then standard mode will work. And so I would recommend that if you're upgrading an application where you've already got code written and it was already utilizing standard PGN mode. If you're starting from scratch, I would suggest just go ahead and configure extended PGN mode. That'll give you the ability to configure up to 32 transmit and 32 receive PGNs. And that's just selected with a checkbox. In terms of your control and status variable, or your control structure variable as we call it, that performs several functions. Each function is performed by one or more words of information, and you'll see them listed here. Okay? And then on the next slide, I've got more details on what each of those control structure variables do. So you've got the first variable, which is a word, but the least significant bit of that word can be used to actually start or enable J1939 communications with the OCS. We've also got another word allocated, one bit at a time, that you can use to trigger a remote message request, okay, for those types of messages that have to be requested. We have another word of triggers that will be used to trigger outgoing messages. We've got a status word that I'll talk more about in a second. And then we also have some registers available or variables available for monitoring which messages have been received, and of the messages you've configured, which ones have been received from a count standpoint. The same thing is true on the transmit side as well. So this is the control structure variable. Really a series of word type variables is what you're looking at here. In terms of details on the status register, that's what you're going to monitor to make sure the health of the network is good, to make sure things are communicating as appropriate. If you have configured a receive message incorrectly or configured a transmit message incorrectly, you'll get a fault here. If you have a transmit message you've sent out that's failed, you'll get another fault. A whole variety of diagnostics are available here. Okay, so once you've configured in general J1939 for the baud rate, you've assigned the control and status register set. Next, it's time to configure or prepare the OCS for receive PGNs and transmit PGNs. Let's start with the receive PGNs. So every PGN that you receive in, as well as every one that you send out, requires 6 words of variable space be allocated to it. If you're using the extended PGN capability, you've got 32 PGNs you could receive, each taking 6 words. So 32 times 6 is 192 words would need to be allocated to the act of receiving PGN messages. Now, if you're talking about register-based logic, you're just going to configure the starting register, and the next 192 would be allocated for receiving PGNs. If you're talking about a variable-based application, you're going to assign a word type variable and dimension it as an array for 192. Okay? So either way, the end result is 192 consecutive words that are allocated for the process of receiving in PGN messages. Okay? Next, you would start the process of actually adding in individual PGNs to be configured for reception. And you can see we've got the details on what's required in all these different fields, as you configure each individual PGN, and you can configure up to 32 of those. Let's start at the top center and we'll kind of work our way around. First of all, you need to enter in the PGN number. That is the identifier for that particular PGN that you would get out of your list of PGNs and SPNs. All right. Next to the right there is priority. Priority is set between 0 and 7, with 0 being the highest priority and 7 being the lowest priority. Now, when you're receiving in messages, priority is not a factor, so you can just leave that at 0. Proceeding over to the right is the broadcasting node, or the source address as it's called on the screen. Okay, so the source address is the node address on J1939 for the device that's sending the data. And that's important. That does need to be configured. Now, typically, an engine control module is going to have a J1939 address of 0. So the default of 0 actually will work quite a bit of the time if you're getting the data from an engine control module, for instance. Okay? And then, moving over to the left, you have the opportunity to put a convenient name for this PGN. Now, it doesn't have to be anything specific, but what I typically do is I'll type in the description of the PGN that I find from the spreadsheet. I'll type that in here under the name. And then what size is the PGN you're going to be receiving? Most of them are going to be 8 bytes, but not all of them, so check your list. And then the last thing to configure is whether it's a broadcast message or whether it is a message that has to be requested. So if it's broadcast, you can leave it at the default radio button setting, as you can see there. If it's not, if you have to request it, then you'll also have to fill in the frequency in terms of number of milliseconds that you're going to request that it be rebroadcast. Okay, so that's the configuration for an individual receive PGN, and you have up to 32 of those that you can configure. Okay, the transmit PGN configuration process is virtually identical, so we're going to go through this quickly. Okay, again, you need to allocate either 192 consecutive registers, or in the case of variable-based ladder, a word-based array of 192 elements. Okay, so that'll be allocated for transmitting PGNs. And then once you're done doing that, every time you want to add a new transmit PGN configuration, you hit the add button. And then you have very much the same fields that need to be filled out for a transmit PGN. What's the PGN number? What are you going to name it? What priority does it need to have? And this is a case where, since you're transmitting the data, the priority field does matter. Transmitting node, that's the node number of you as the OCS. And that's not necessarily, that's not the CAN address, that's the J1939 node address. Okay? And then again, I forgot to mention this on the receive side of things, but whether you're receiving or transmitting data as a PGN, you have to allocate the data that's going out or coming in, and you do that through a variable. Either 4 consecutive registers or a word array of a size of 4. Why 4? Because 8 bytes of data, which is typically, but not always, what you have in PGN in terms of data size, 8 bytes correlates to 4 words. And you have to allocate a word type variable to this particular dialog box, whether you're transmitting or whether you're receiving PGNs. Okay, so that's the configuration process. So enough of these slides. Let's go ahead and fire up Cscape. And let's go ahead and show you how we would configure that in Cscape. All right, so what I have here is I have a program that I've already created, but I'm going to go ahead and save that for later, and we'll review that later when we get into the other parts, the other aspects of J1939. What I'm going to do here is I'm going to create a new program, okay, and show you how to configure J1939 from scratch. Because everything demo-wise that I have done today is all in variable-based ladder, I'm going to go ahead and use register-based ladder for this little short demo, just so people can see how that contrasts with variable-based. But it's very, very similar. Okay, so I've started a new project. I start by going directly to the hardware configuration. Okay, I select the controller that I'm going to use in the application. In this case, I've got an XL7. All right, XL7 on port 2 can support J1939 right out of the box, so I can go ahead and select J1939 here and hit the config button. All right, so we start at the network level. Which default message database are we going to use? We're going to use the default there. In the future, we'll have more options. Today, the only really good option is manual definition. Network baud rate, our choices are significant, as you can see here, but 250K is the default in most cases. All right. Next, we have to decide, do we want to enable extended mode with up to 32 PGNs both directions, or live with standard mode, which is 15 PGNs both directions? Let's configure extended mode if we've got a new application. I'll allocate, because this is register-based logic, I'll allocate just register 1 here. And down here, Cscape details for me what each of the 10 words in my control structure is going to be used for. Okay? All right, so that's all the configuration I need to do on the network level. Now I have to prepare the OCS to receive and to transmit PGNs. So under receive PGNs, this is where I have to allocate 192 words of variable space for the process of receiving in PGNs. So to keep this simple, I don't have to type in the %, although I can if I wish. I'm just going to go ahead and allocate a register 1001 here. So that means that register 1001 through 1192 will be allocated towards receiving in PGNs. Again, I've got my options down here that I will always leave at the default at this stage in July of 2021. Okay, so that configuration is complete for receive PGNs, and just like transmit PGNs, I do something very similar. I need to allocate 192 words of variable space for the transmitting of PGN data. Okay, so that's all there is to the configuration, the basic configuration of the OCS for J1939 before we actually start the process of adding specific configuration settings for receive PGNs and transmit PGNs. So let's leave that there for now, and when I come back, we will definitely cover configuration from a variable-based setup, as well as adding an individual configuration for receive PGNs. Okay, so that's all of our Cscape demo for now. Let's go ahead and go back to our slides. So next, let's talk about what happens once the PGN data starts coming in. Okay, what are we actually going to do with that data to get the information we're looking for? So effectively, once that PGN data comes in, and it's almost always going to be 8 bytes, you're going to need to isolate the portion of that PGN that contains the SPN data that you're interested in. Okay? And there are some logic instructions that are very handy for this that in some cases we don't use for a lot of other functions, or at least not frequently, I'll put it that way. So I thought it was important to kind of review these with you today, because a lot of what you're going to be doing with J1939 is extracting the data and massaging it from the PGN. So let's take a look at an example here. Let's say that the data we're interested in, let's say this is an excerpt from a PGN. Okay, so this is 2 bytes out of the 8 bytes that came in from the PGN. And let's say the specific SPN data we're interested in is the 8 bits of data in yellow. We want to keep that information, massage it into the engineering units that we want, into the data that we want, but we want to throw away this extra data that was transmit as different SPNs, that we received as different SPNs in the same set of data here, or in the same word of data. Okay, so how can we keep part of the data and discard the rest? Well, to do that, we use a function called a bitwise AND. The way a bitwise AND works is that it goes bit by bit, place by place, and we're looking at this in binary, and it ANDs each bit with the next one. So in the ones place, it's going to AND that first bit in the ones place for the 2 words that make up part of the instruction. Okay, so what we do in a bitwise AND to isolate what we're interested in is we AND the data we have, putting zeros in where we want to eliminate, and putting ones in where we want to keep. And we do that because any bit ANDed with 0 always returns a 0. and any bit ANDed with 1 returns that same bit we started with. So if we go ahead and AND that bit pattern with what we have in this example, we're going to get at the bottom there the data we're interested in yellow, and just zeros on the outside, which is what we want. Okay, that's at least the first step of what we want. So what is that bit pattern in the middle that'll get us that result? Well, in this particular case, for those 8 ones in the center there, that's equivalent to 4080 in base 10. Okay, so if you did the conversion from binary over to decimal, you'd see that's 4080. So in Cscape, when we do the AND function, we're going to take that data in that word that we've received in, we're going to AND it with 4080, and then that result is going to be what you see below with the data we're looking for in the center. The only problem is the data that we have at the bottom there in the center is not going to be interpreted properly if we just leave it that way, because all that data is in the middle of the word, and it really should be aligned with the right side of the word so we can interpret as a proper decimal number, for instance. Okay, so what can we do to shift that data where we want it? Well, we can use divide and multiply commands to shift either up or down. If we need to shift data up towards the most significant bit, we can use the multiply function. If we need to shift down, we can use the divide function. So that's what we use if we need to shift. All right, and this is all very common things you need to do with J1939. Mask off the data you don't want, shift the data you have left to make sure it's aligned properly. Okay, so in this case, if we want to shift those 8 bits over to the right 4 spots, we need to divide by 16. Why by 16? Well, to shift over 1 to the right is divide by 2, another one divide by 4, another one divide by 8, another one divide by 16. So 4 spots we divide by 16. Okay, and then in the end, we end up with what you see there, and that is the data we're interested aligned properly with the least significant bit, so we can interpret it as a standard decimal number. So that is a couple of functions that you're going to use frequently with J1939, that being the bitwise AND function and then the multiply and divide functions for shifting. The last part of our program today is all going to be about demonstrating how would we accomplish this in a real-world application. So what we're going to do first is we're going to take a look at a particular SPN that we're interested in, one that's called engine coolant temperature. You can see it highlighted there in yellow. So that's SPN number 110. It's part of PGN 65262. Now you'll notice that within PGN 65262 there are 6 SPNs there. Okay? Now in terms of where they're located within the 8 bytes of data, that's determined by the position column or POS column on the screen there. So the one I'm interested in, thankfully, is right up front. It's located in the first byte of data in that SPN. However, it's only a byte in length, and there's more data starting at byte 2, so we'll have to deal with that properly. But anyway, this data is going to come in as a byte. We're going to need to strip off the data we don't care about in the other byte, and then this data will need to be adjusted or scaled to the appropriate temperature range, and in the case of this particular parameter, as you can see from the offset column, we're just going to be adding a -40 to the data to get our degrees Celsius result. So if we want the engine coolant temperature, we can get it from PGN 65262 using SPN 110. So this is the type of information that we need before we start programming the OCS. So let's get into Cscape now. All right, I'm going to go ahead and shut down this quick demo program that I did for showing you how to configure the J1939 using register-based logic. Now I've got my program that I've pre-configured to deal with a couple of PGNs. Now let's start at the configuration level. So again, I'm going to J1939, go to the configuration. Let's take a look at how we configured this. So on the network level, we left the defaults. We set it 250K, for the baud rate. And here is our control structure variable, which happens to be a dimensioned word variable with a dimension of 10. Okay, so 16 consecutive words, and here are the details as to which member of the array, what its function is from a control and status standpoint. And of course, the same information with a lot more detail is also available in the help file. Now, from a receive PGN standpoint, we have allocated 192 words using a word type variable array with 192 members. The first member is listed here, and I just happen to name it J1939 underscore PGN underscore RX, and the first member is sub 0, and it goes all the way to sub 191. So same thing, almost identical. On the transmit side of things, I've assigned another similar but different variable to allocate 192 words of variable space for the process of transmitting PGN as well. Now let's take a look at the details of the two receive PGNs that we have received. And we're going to start with that very first one that we're working on here, and that is our engine temperature. So quickly, let's go back to our slides and take a look at the key information here. We need to know the PGN number. That's the first piece of information we need. That's really the main and really only piece of information we need for now, is the PGN number. So PGN number is 65262. A good description that I typed in is engine temperature 1. That happens to be the equivalent to the standard name for engine temperature 1. Okay. Priority is not important because we're receiving the data in, and that is handled by the transmitting node. Source address is important. It is coming from node address 0, so I didn't just leave it at blank. It happens to be the proper node address. Destination address is not important in this case because this is a broadcast message being sent onto the network. And then data size that we're receiving in is 8 bytes. And this is the variable array that I've created, which is a word type variable with a dimension of 4 words, sub 0 through sub 3. The reason I chose 4 words is because 4 words lines up with 8 bytes. And again, this is a broadcast type message, so monitor mode is what is selected. It's not a message that I have to request. Okay, so that's all the configuration that was required to configure this first receive PGN. Now let's go ahead and take a look at this guy in action. So let me go ahead and fire up my XL7 here. So let me switch to the overhead camera. Okay. All right, so what we're looking at here is I have my XL7 running the program that I just reviewed with you, and we're taking a look at this first PGN, 65262. So you see it right there. Okay. And what I've done for illustrative purposes is I've lined up the data that we're receiving in those 8 bytes into those 4 words of variables. And they're lined up right here, as you can see. Now, the first thing you should notice is a lot of FFs, and really only one nibble, if you will, that's actually changing. What are the FFs all about? Well, in J1939, it's very common that when you receive in a PGN, it'll contain multiple SPN parameters, but it's very common for a lot of those other SPNs maybe not to be supported. So any SPN that's not supported will report a value of FF. So FFs are to be expected and normal as long as they're not in a parameter that you were hoping was supported. So in this case, this PGN 65262 that has 8 bytes of data, it's really only the very first SPN in that lower byte of byte 1 that's actually active. Okay, but as you can see from looking at that first variable word, which is currently FFE1 and counting down, the data we're after is in the lower half of that first register, byte 1 to be exact. If we're going to convert that to a decimal value that we can use in our program, we need to strip off the part we aren't using, which is the upper byte of FF. So to do that, what we're going to do is in our program, we are going to take our data in that first register and we're going to AND it with 00FF. What is 00FF? Well, it's all ones in the lower half to keep all that data and all zeros in the upper half to get rid of all that data. So our end result after we do that is 0069 or whatever you can see here. The data we're after is in the lower byte. It's in hex here. I've also shown it in decimal there. And then the very last step is to scale it to temperature, which in this case, it's already in temperature. It just needs an offset applied. We do a add -40 to it to get our value. So the value we're after here is the coolant temperature. And here's how it came in. Here's the processing we did on it and the scaling we did on it. Now let's take a quick look at the code required to make that happen. Pretty simple stuff. All right, I'll say OK and OK. And then I will take a look at the logic that's used to process that PGN. And it's really very simple. We've got a single AND block where we're ANDing the data, that first word of data that came in from the PGN. We're ANDing it with 00FF hex, which happens to be 255. The result of that goes into another variable, which we're calling coolant temperature raw. The reason it's raw is because it's not had the offset applied to it to get it to line up with degrees Celsius. The next function block adds -40 to do that offset and creates our coolant temperature variable. So that's really all there was to it. This is a really easy one from a J1939 standpoint to deal with. Let's go back to our slides now, and let's take a look this time at the next PGN that we want to actually deal with. Okay? And this next PGN isn't going to be quite as simple, but in this demonstration I wanted to show you a little more difficult one because I figure if there's a difficult one to deal with and you can see how that's done, you'll be able to handle any of them that come your way. So with this one, what we're interested in is engine speed in RPM, and I've got it highlighted there. So that is SPN number 190, that's all part of PGN 61444, okay, and the name of the PGN that it's coming from is Electronic Engine Controller 1. So that's really what we're after. So let's head into Cscape and let's take a look at the configuration of that received PGN. So back to hardware configuration, back to J1939 configuration. Let's take a look at the receive PGN configuration for this guy. So here's 61444. Here's the description we put in. Again, priority is not important. We're receiving the data in. Source address is. It is coming from address 0. Destination address is not important in this case. And again, we're in monitor mode. And here's the 4-word variable, or a word type variable with a dimension of 4 that I named PGN 61444. That's where the data is coming in. Okay, let's go back to our XL7. All right, I'll move that up here. Back to our XL7, and we're still looking at that previous data for that coolant temperature. Let's switch over to this screen where we're taking a look at this PGN, where we can extract our engine RPM. Okay, just like last time, I have isolated the data coming in from that PGN over here. So here's the 8 bytes coming into those 4 word type variables. But this time you'll notice that the data we're after, which going back to the slides, the data we're after is 16 bits long. It's made up of 2 different bytes, but those 2 bytes are located in 2 different words. So the least significant piece of data is here, and the most significant piece of data is here. So we've got a little more work to do with this one. Again, I wanted to show you a fairly complicated one. But the process is the same. We start by isolating the bytes that we care about, or the data that we care about. So in this variable, we're going to AND it with FF00, again, to keep everything on the left and to get rid of everything on the right, and we end up with the data we want on the left and zeros. We do the same thing down here. We're interested in this data. We mask off the top by ANDing it with 00FF. All zeros on the top, all ones on the bottom, and then we get our our data isolated. Now the problem we have is this is supposed to be my least significant byte. This is my most significant byte. You see, they're in the wrong location. So I need to shift this guy down and this guy up. So I use my divide function to shift this guy down. I use my multiply function to shift this guy up. All right, so now what do we do? Well, we've still got the information in two different words. How do we put them together? Well, we just use the add function. That's nice and simple. So we add this guy, and our result is in this variable here. Now, the only thing that's wrong with this variable here is it has not been scaled to RPM. In the case of this particular parameter, the scaling that we need to do is over towards the right-hand side there. You see under resolution, it's 1/8 RPM per bit. So that basically means we need to take that value that we've created, our raw value, and divide by 8. All right, so back to the OCS, and you'll see that we took that raw value, we divided it by 8, and I'm showing it here in decimal. Okay, so I wanted to spend a fair amount of time on showing you not only how to quickly configure to receive in PGN data, but also some of the operations that you might do to process it once you've actually received the data in to get out that SPN data you're interested in. One last thing before I bring Casey in. At the top of both screens, I did have some of the status information shown. So this is actually the enable bit, which allows me to start and restop. Oh, doesn't like something. Anyway, that's the bit I would use to stop and restart the network. There's my status. There's indication that I've received messages in and the fact that I've received in 2 messages. Okay, I think I know what's wrong here. I think I've configured that for a momentary or something. Okay, let's go ahead and bring Casey in. All right, Casey. So that was probably more bitwise AND functions than you've used in a while, I'm guessing.
Absolutely, for sure.
So people probably thought those were so old-fashioned that nobody ever used them anymore. Well, sometimes you need to massage data in a little different way, and using bitwise ANDs and divide and multiply, you can get that accomplished.
Yeah, it's highly useful. We did have one question came across. That was early on, kind of, I think, in the general message definitions from Joe. He's asking, what's the reason for a 64-bit SPN? Something, it seems like a lot of data just to show something like our RPM. Okay,
sure. Well, basically, it's because J1939 was built on CAN. And remember about the characteristics of CAN. Why not just use some different network? Well, the CAN chip that J1939 is based on is extraordinarily noise immune. It works in just nasty environments. And think about some of the environments for vehicles, whether you're talking a car, a dump truck, a crane, we're talking a cement truck, we're talking some really nasty environments. So what you need above all else is you need a robust network. And CAN is that and more, okay? Now, what CAN is not is a network that has a ton of space in the payload of messages. The messages are relatively small, quite small actually, only 8 bytes in size. So the goal of CAN, or the goal of J1939, was to pack as much data as possible into 8 bytes of data. So that's why we have to go through this extra effort to unpack some of those parameters. Whereas with a newer network where you're running in a different scenario, with some sort of Ethernet protocol where you have humongous payloads, you would just stuck every parameter in a different register and not worry about it, right? But you've got this data being transmitted in a very rugged environment, and you want to take advantage of what you have. Now, one thing to be aware of is that there is a new standard moving forward for CAN that over time will be applied, and that's something called CAN-FD. And CAN-FD expands greatly the amount of payload that can be accompanying a CAN message, well above the 8-byte norm. So the long answer there for that question was, why did they cram so much stuff into that register or into that 64 bits or those 8 bytes when all they cared about was RPM? Why don't they just put it in its own separate packet? That's the reason.
We got
Sure.
in. I think it's let's see, it's from Marlon asking, do you guys support databases?
Do we support databases? We don't have a direct database support at this stage. Let me describe how we do support it today. This isn't directly related to J1939, but that's no problem. We love to answer questions in general.
Yeah.
So today, any connection with OCS data to databases is made outside of the OCS. So there's tons of ways to take OCS data, extract it out of an OCS, whether you're talking about OPC or whether you're talking about SCADA or some other means, whether you're talking about MQTT. There's lots of ways of getting data out of an OCS into a server of some sort. Okay, and then once it's on that server, whether you're talking OPC or something else, then it's relatively easy externally to get that data into a database. But that is done outside of the OCS. Now, we are working on, for 2021, we are working on kind of a database option for Cscape 10. Okay, but obviously Cscape 10 is not even out yet, so the database option is down the line a ways. But that is something that we have planned for Cscape 10 on down the line, some tighter integration with databases. But for now, just get the data to a server using one of the normal means. Once it's on the server, use a third-party package to connect it up to a database.
Alrighty, well, I don't see any more. I think that just about covers it.
All right, well, if something comes in while we finish here, let me know. Go ahead and interrupt. We'll come on back. Okay, let's go ahead and mention that every Tuesday, you'll find us here on YouTube at 2 o'clock Eastern Time, and we'll have another new topic for you, which we'll try and cover in an appropriate amount of detail. July has been a busy month. We've covered Cscape Security, User-Defined Function Blocks, J1939 today. Next week, Analog I/O and the Micro OCS. So specifics about Analog I/O. The Micro OCS has the capability of doing field calibration. It has a little different analog than we've done before in terms of its ability to share terminals between analog outputs and RTD inputs. So we'll explore all those sorts of things next week with Analog I/O and the Micro OCS. And another thing I also want to mention, and that is, as I bring Casey back in one more time, I want to also mention, and that is that last week we announced the fact that we were starting or opening up training classes for 2021. So we have a September in-person training class that's already full. Now, that's obviously, you can see how popular that's been. But we also have our October 12th and 13th virtual online training course, which will absolutely be hands-on, and the training equipment is yours to keep that's built into the tuition. So keep that in mind. There's still plenty of seats available for virtual training October 12th through the 13th. Okay, also don't forget, subscribe to the channel. Certainly you'll get notifications if you ring the bell that tell you when we have live streams available, that tell you when we have more content posted. There's some real advantages there. And again, don't forget to join us every Tuesday, and next Tuesday specifically for Analog I/O in the Micro OCS. Everybody take care, and we look forward to seeing you next week.